This section is about binomial and geometric random variables, and actually today we're only going to talk about the binomial random variables. So a binomial random variable is a random variable that's going to satisfy 4 conditions. And the 4 conditions, you can remember them using BINS, B-I-N-S, are going to give you your 4 conditions. So my first condition is that it is binary. And by binary, if you remember the meaning of the prefix bi, it means 2. So what that means is that I have 2 possible outcomes. And it's only going to be 2. If you have more, it's not a binomial variable. So my 2 possible outcomes, we call them a success and a failure. So the second condition of a binomial random variable is that your outcomes, your trials, must be independent. So what's going to happen is that if you know what happens in one trial, that's not going to affect what's going to happen in future trials. So you probably have heard the phrase independent before in this class. And it just means that things don't affect each other. So we're going to say that knowing one trial's outcome doesn't tell you what will happen with the other trials. So then my third condition is that there is a fixed number of trials. So it's the number condition. So there's a set number of trials, and we call that number n. So there's a fixed number of trials, which we call n, and this is set in advance. And the last condition is called the success condition. And what I mean by that is that each trial has the same probability of success. And we call that probability of success a lowercase p. So you're going to see the letters n and p frequently in this section. So for these examples, we want to know whether the random variables below have a binomial distribution. And I specifically asked you to justify your answer. When I ask you to justify your answer, whether something is binomial or not, you're going to look at the 4 conditions we have above. So let's look at them one at a time. So first of all, the binary condition. So my binary condition means that I have 2 possible outcomes, and I do have 2 possible outcomes. So my 2 outcomes in this case are what I call a success, which means I get what I want. I want to get a 6, and you can tell that because this is telling you that we're looking for the number of 6s. So success means I roll a 6. A failure means I roll something else. So even though our variable is defined as the number of 6s, actually we're either going to get a 6 or we're not going to get a 6. Those are going to be called our success and failure. We don't care about any numbers other than 6. 1 through 5 are all going to be grouped together in 1. Okay, so the next thing is the independent. And these are independent. The reason they're independent is because the 2 rolls are not going to affect each other. So 2 rolls of a die don't affect each other. And that's a general thing when you're rolling a die. You're not going to have anything causing something else to come up more likely than another roll. My third one, the number condition. And I do have a fixed number. I specifically said roll a fair die 10 times. So there is a set number, and my number is going to be 10. And we're actually going to use the n equals 10. You're going to use that later on when you're looking for actual probabilities, when you're actually calculating things. The fourth condition is each trial has the same probability of success. So actually, in this case, my probability of success is my p. I said the success is getting a 6. There was a 1 in 6 chance of that happening. So this one looks good. This one, the B checks out, the independent checks out, the binary checked out, the independent checked out. There's a set number, and there is a set probability of success. The probability of success is the same for every trial. So in this case, we say that this is a binomial random variable. Okay, so for number 2, we are shooting a basket 20 times from various distances on the court, and our variable is going to be the number of shots made. So in the beginning, my binary thing, that actually works. So my binary aspect of it is a success, in this case, is making a shot. My failure is missing a shot. And independent is sometimes tricky in a situation like this. But in this case, we're going to assume that the person that's shooting isn't going to like get flustered by missing one, and that's not going to cause them to miss more in the future. So we're going to assume that they're independent. So in these types of problems, they'll specifically tell you something that might cause things to not be independent. So otherwise, you're probably going to have to make this assumption. You really just have to think logically about this type of thing. So I'm going to assume that making or missing a shot will not affect other shots. Okay, so in this case, there is a set number of shots, and they tell us we shoot a basketball 20 times. So n is 20. Okay, we have an issue with our success. They do not have a probability of success. They don't give us one, which doesn't mean that it's not going to be that we don't have one. However, they specifically tell us that we're shooting it from various distances. We can assume that shooting from like way past the 3-point line is going to give us a very different probability of shooting very close or doing a layup. So we have no way, we cannot say that the probability of success is going to be the same. So the first 3 actually checked out, but the last one, it's not going to be the same for every trial. Because of that, we're going to say, so that one's not going to work. Because of that, we're going to say that this is not a binomial random variable. Okay, so for part C, you might see something right away that's a little bit sketchy, the binary part. So binary means that there's 2 possible outcomes. However, with colors, there are a whole bunch of different colors of car. You could have red, you can have black, you can have white, you can have silver. So in this case, there are more than 2 possible outcomes. This is already going to fail being binary. So we are going to immediately have a problem here. We know it's not binary. You might want to check the other ones just in case, just for practice. You will find that it is, so I'm going to put an X there for the B. You will find that colors of cars are independent. They're not going to affect each other. There is a set number. The N works, so the independent is going to work. There is a set number, which is going to be 100, so that one would work. The probability of success, we actually can't even figure that out. We would assume not, but since we don't have a set success, that one's not going to work at all. So this is not going to be binomial. Once we fail on one of these, it's just not binomial at all. So from the beginning, we knew it was not binomial. For our first example, we want to know about rolling doubles in a game. So I'm thinking most people have played Monopoly, where you need to roll doubles to get out of jail. Basically, all it means, if you haven't played it, all doubles mean is that you get the same number on both dice. So you're rolling 2 dice at once. So the probability of rolling this is going to be 1/6. So what I'm going to do is I actually even told you this, X is a binomial random variable with N is 4 and P is 1/6. The first question I asked is, what is the probability that X is 0? What I mean by this is, what is the probability of getting no doubles? And in that one, they told us we're looking at 4 rolls of the dice, so we want to know the probability of getting no doubles in 4 rolls. There's actually a few ways to do this. In a minute or two, I'm going to give you a formula, but before that, we'll do this one by hand, and we'll also do B by hand. So for this one, what you're looking for is you want the first one to be not a double. You want the second roll to be not a double. And you want the same thing for the third and the fourth, which is very unfortunate if you're sitting in jail in Monopoly. So that we want to know the probability that this happens 4 times in a row. So actually in this case, they told us the probability of success is 1/6. So this right here is the probability of success. What we're looking at is 0 successes. We want to know the probability that we fail 4 times in a row. I'm going to actually write this just as an F to show that these are all 4 failures. And what's going to happen there, your probability of failure is going to be 5/6. You just subtract it from 1. And we want to know the probability that these happen 4 times in a row. You get this by multiplying 5/6 by 5/6 by 5/6 by 5/6. So you end up with 5/6 to the 4th power. And that gives you 0.482. So there's actually a fairly high probability of that happening. Okay, so the next one is looking for the probability that X equals 1, which means that you get 1 double in 4 rolls. This is unfortunately a deceptive problem. It seems like it's going to be very easy, but it's not. So I'm going to show you what people want to do. What people want to do is they want the first thing to be the probability of getting a double, which we know is 1/6, times the probability of not getting a double, which is 5/6, and then multiplied by 5/6 another few times. What I'm going to do, rather than writing out no double, and no double, we want the probability of a double. That's our success. No double is a failure. Another no double is a failure, and this one's also a failure. So this is the way that most people try to do this problem. And that actually is going to get us partway there. The big issue with this problem comes in that you could get your double the first time around. You could get a success the first time around. But it can also happen that you fail the first time around, you don't get a double, and then you get a double the second time. Or you can fail the first 2 times, your success will come on the 3rd roll, which is going to be your double, and then you fail the 4th. Or you can get 3 failures in a row where you don't get a double and then finally get one on the 4th turn. So actually, this problem does have a little bit more going on than what I wrote above. There are going to be 4 possibilities here. So what you're going to have to do is you're going to have to take what you have up there, the 1, 6 times 5, 6 times 5, 6 times 5, 6. You need to multiply that by 4, which is your number of possibilities. So in the end, you are going to get 4 times 1 over 6 times 5 over 6 to the 3rd. And your answer does end up being 0.386. So if you see this type of problem, just know it's probably more difficult than you expect it to be. It's probably there to deceive you a bit. If you're working with binomial random variables, you're always going to have to do a little bit extra for most of these problems. The good thing is that you don't have to be calculating all of these or writing all of these possibilities out every single time. We have a formula that's going to be very helpful. So this is our binomial probability formula. It looks pretty scary, but actually once you get the hang of it, it's not so bad. If it really bothers you, after we do a few examples on it, I'll show you a way to do it on your calculator also. So what we have is we're going to call x a binomial random variable. My total number of trials is n, and I'm going to call p my probability of success. So what I'm going to have is that the probability that x equals k, the k is the number I want. In the previous example, you might remember, we wanted to get doubles exactly once. So k in the last one was done. Was 1. The n is going to be the total number of trials. So you might notice this first thing, the n, it looks like n over k almost. This is called the binomial coefficient. And I don't know how many of you remember factorials, but just a little recap. If you have something like, for example, if you have 3, the exclamation mark is called a factorial, 3 factorial. You just do 3 times 2 times 1. Which gives you 6. So that pattern's going to work for all of them. There's going to be a few ways to simplify it a little bit. If that's new to you, it's not too hard. You're just doing like 4 factorial, for example. You do 4 times 3 times 2 times 1, which gives you 24. And as you do more of these, you'll find ways to simplify them out. So let's go ahead and do example number 3. So we're still rolling 2 dice, and we still have a probability of rolling doubles as 1/6. And we're still going to roll dice 4 times. For A, we want to know the probability the player gets doubles twice in 4 attempts. So in this case, my n, my number of trials, is going to be 4. My P, they already told us the probability of success is 1 over 6. My K is going to be what I want. I want to know about getting doubles twice. And just a comment, this P, the 1 over 6, is a lowercase p. You'll notice that the other P that we have in the problem up there is uppercase. I'm going to write that down. So just be careful that you know that these are 2 separate things. So I'm going to go ahead and take my formula, and I'm just going to put in numbers now. So I'm looking for the probability that x equals 2. This means the probability that the player gets doubles twice in 4 attempts. So my first thing I'm going to use is my binomial coefficient, which I'll find in just a minute. I do that times 1 over 6 to the 2nd times 1 over 1 minus 1 over 6. And it's going to be to the 4 minus 2, which thankfully is also going to be to the 2nd. So what's going to happen now is I have something kind of long to work out. It's not impossible, but it's not easy either. It's just a little complicated. I'm going to now use the formula from above. I have 4 factorial over 2 factorial over 4 minus 2 factorial times 1/6 squared times 1/5 or 5/6 squared. So if you want, with the factorials, you can write them out. You'll find tricks to make them faster. So 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. This other one is going to be 2 also. So I also have times 2 times 1. If you want, you can simplify some things out. Like the 2's can cancel, the 1's will cancel. You end up just getting 6 in the end for that. So, and that's times 1/6 squared times 5/6 squared. So I'm just going to end up with this being 6 times 1/6 to the second times 5/6 to the second. My final answer, and I recommend that you work this out on your calculator to make sure you're doing okay. So my final answer is going to be 0.116. All right, so for part B, we're looking for the probability that the player gets doubles more than twice in 4 attempts. What that means is I'm looking for the probability that x is greater than 2. So what that means, I need to do probability that x equals 3 plus the probability that x equals 4. You'll notice I'm doing some things that were similar to the last section, except there's a little bit extra going on. So I'd like you to try this next stuff on your own. See if you can get it on your own. You're welcome to pause it and then try it out, but I'm just going to write out the formula and then I'm going to have you work it out on your own. So you do end up getting the binomial coefficient 4 and 3. We call this 4 choose 3 actually, in case you're wondering. And we get that times 1/6 to the third times 5/6 to the first plus 4 choose 4 times 1/6 to the fourth and 5/6 to the 0th. So please try to work this out on your own. Your final answer should be 0.016. It's very unlikely to get. So we're going to skip example number 4 for now. That one, it's really painful to do unless you have a calculator to do it with. So we're going to do it together in class, and I'm going to show you how to solve it on the calculator. So I'm going to give you the ways to find the mean and the standard deviation of a binomial random variable. Actually, if you look down at example number 5, you can probably find the mean and standard deviation on your own without these formulas I'm going to give you. But the formulas I'm going to give you are going to make it a lot faster. So I'm going to call the binomial random variable, I'm just going to call it x. So my mean, or my expected value, is mu sub x. All you need to do is n times p. The standard deviation of that is going to be the square root of n times p times 1 minus p. So let's do this example for number 5. So you are 100% welcome to calculate the mean by itself. And you do not need to write this down, but if you were to do that, you would get 0 times 0.482 plus 1 times 0.386, and so on. So you could multiply that whole thing out, and you can work it out if you want to. However, using that formula is much nicer. They give us n is 4, they give us p is 1/6. So all you're going to do for this one is you do 4 times 1/6. If you don't believe me that this formula works, you can definitely try the other method. You do end up getting 2/3. The other thing I want you to notice is that some of these values we actually calculated out earlier. Like we calculated out 0, we calculated out 1. So hopefully those should look familiar, assuming that you looked at the other part of the notes. So then the last thing we're going to do is the standard deviation. And this one, I highly recommend that you use the formula. You can do it by hand. I do not recommend it. It will take a long time. So you're going to do the square root of 4 times 1/6. 1 minus 1/6 is 5/6. And you just multiply that out. Your answer is going to be 0.746.